be on the exam next week. Yep.
The exam next week then is chapter 5 and 11, or?
And 10, acids and bases.
10 and 11?
And 5.
5, 10.
5, 10, and 11.
Okay.
It'll focus on those 3 chapters, and there will be a little bits from other chapters sprinkled in there too. But the major focus will be those 3 chapters.
5, 10.
And not the whole 11. We'll see. I'll show you where we stop at the end of class today. All right, so the last thing we're going to talk about today before the exam are some new functional groups on organic compounds called alkenes. So we had alkanes, now we've got alkenes. Alkenes are double bonds. So when 2 carbons are sharing 2 pairs of electrons instead of 1, you get something like this. So the smallest possible alkene is this one. So you got a double bond between 2 carbons. And the name of this molecule is ethene. Sometimes it's called ethylene, but if we're following the rules, the name should be ethene. So notice the only difference here is that E. If it were 2 carbons with 6 hydrogens, it would be ethane. Now 2 carbons with 4 hydrogens and a double bond, it's ethene. So this gives you a clue as to how we're going to name these things when we get into that. Alkenes have a different structure than alkanes. Take a look at one here. Here's a molecule of ethane with its 3 carbons on each, or 3 hydrogens on each carbon, so CH3, CH3, and you see that tetrahedral 3-dimensional structure that we talked about before. So now if we add a double bond instead of a single bond, we have 2 fewer hydrogens, and we also change the geometry. So now this molecule is flat. It no longer has that tetrahedral 3-dimensional shape. It's now flat and planar. All those atoms are in the same plane. See that? And the name for this is trigonal planar. That's not so important, but you can picture it like a triangle. So this would be in the center. If each carbon is in the center of a triangle, then the things it's connected to are at the points of the triangle. And so that makes this bond angle about 120 degrees. So this molecule is flat. The name for that is trigonal planar, 120-degree angles. Everything has that triangular 30-degree angle. And then another interesting thing about alkenes that's different from alkanes is that a double bond between 2 carbons does not rotate. And that opens up some interesting possibilities for how these can be a little bit different from the alkanes that we saw before. So let's look at a couple different structures. If I drew two things for you, these two structures, this is something we did kind of last week. Are those two the same or are they different? They're the same. How do you know? So you got 4 carbons in a row, connected one right after another with no branching or anything. And they only differ by rotation around that central bond. So if you kind of like imagine that in physical, like a physical copy of that, you kind of twist one side of it up, you have the other one. So that they only differ by that rotation. And so with single bonds, with alkanes, we would say those are the same. If we throw a double bond in there, though, things change. Now these are different. And they're different because you can't twist that double bond. It's locked in place. And so you can no longer say, well, if I just flip this one side up, then I've got the same thing as the other, because they're actually not the same. Because they're not the same, we need to come up with a different way of naming them. So let's talk about how to name alkenes, and then we'll get back into that, talk about how we can distinguish those two. All right, so a couple of important differences when we're naming alkenes. First of all, we haven't really talked about reactions, and we aren't going to get into reactions until next week after the exam. But those alkanes, all those molecules we've been dealing with, are not terribly reactive. They can be burned, they can do a couple other things, but they mostly don't really react. The ones with halogens do, but that's a little bit different. When we put in a double bond in the molecule, or we look at this molecule with a double bond, we now have a molecule that is more reactive. Those double bonds can react. And so because of that, the double bond is really important. It completely changes the nature of the molecule and makes it a totally different thing. So the first rule of naming alkenes is that the alkene part, the double bond, takes priority. And that's going to work in a couple ways. First, the double bond is going to be a part of that main chain, if possible. So even if that means that you have to have a smaller main chain instead of a bigger one, that's okay as long as the alkene, the double bond, can be in there. And the double bond should be closest to the end. So we want the double bond to have the lowest possible number, even above the substituents. So with regular alkanes, we said we have to number to try to get the lowest possible numbers for all the substituents. With alkenes, we say the alkene has to have the lowest possible number. Let's look at some examples. All right. Let's take a look at this structure. This is a structure that has an alkene in it, a double bond. If this were a regular old alkane, we would say, all right, the longest chain is 6 carbons right across the middle. That's hexane. And then we've got this substituent coming off, so we're going to start numbering from the right so that it has the lowest number. But with these new rules, we would say, wait, that's not right. The alkane has to be a part of that main chain. So rather than starting at the left end or the right end, we should start at the end where the alkene is. And we should start numbering here and go 1, 2, 3, 4, 5. See how that works to give the alkene priority? Okay. This can also happen in a ring. So let's say we have an alkene here, and we've got like some substituents there. Normally, you'd make position 1 that top of the ring. But in this ring, you can't do that because you want the alkene to have the lowest possible numbers. So instead, you should start numbering down here. And go around counterclockwise so that the alkene can be between 1 and 2. And then your substituents have the lowest possible number, which in this case is 3. So you're always going to try to number to get the lowest numbers on that alkene that you can. Sometimes, both of these examples, the alkenes between 1 and 2, that's not always possible. So like if the alkene is in the middle of the chain somewhere, let's look at something like this. So the alkene's in that main chain already. So we're definitely going to start numbering over on the right side. And the lowest possible number that we can give that alkene in this case is 2. So we can put it between 2 and 3. And so this would end up being like a 5,5 dimethyl. We'll go back and name these in a second. Okay, so then that's the first rule, and that's really the hardest part, is trying to figure out how to number it properly so that we can get the alkenes the lowest possible number. So then 2 put the starting number of the alkene before the name of the main chain. This will make more sense when we do an example. And change the ane to ene. Everything else with substituents and stuff is the same as what we've been doing. So let's take a look at each of these molecules and name them. All right, so we numbered it properly here. We did that before. So now we do everything else kind of the same. We take our main name first. In this case, it's going to be pent because we've got 5 carbons in that main chain. But it's not pentane, it's pentene. And that double bond could be in different positions on that chain. So the fact that it starts right at the beginning at number 1 means that we specify this as 1-pentene. So that's that, put the starting number of the alkene before the name of the main chain. You put that number in there to specify where that double bond is specifically. Then we can add our substituents just like normal. So our only substituent here is this, which is a 2-carbon ethyl substituent, coming off of number 2. So this is 2-ethyl 1-pentene. Okay. Take a look at this next one. Yeah.
Why do we start? It goes by the double bond.
Yeah.
It starts at 1, we were able to go by 2. We're able to pass the double bond. This pending that we don't take the whole structure. Start at where the double bond is. Why aren't we starting at the beginning?
Sure. Like, why don't you start here?
Why are you using the whole?
Why are you using this chain right here?
Correct.
Yeah, because the double bond isn't in that chain. So if we go 1, 2, 3, 4, 5, 6, we're not including the alkene as part of that chain. And because the alkene is so important, it's the most important part of the molecule, it has to be a part of that chain. So that's what's different here. Because it takes priority, if there's any way that you can get it in that main chain, you put it in the main chain, even if it means a smaller overall count. So in this case, yeah, you'd have a longer chain if you go this way, but this way we can get the double bond in there, so that takes priority. So always start your counting at the double bond, or at least with the double bond if possible.
But in the next structure, you're able to use the whole thing.
Because the double bond is in there. Yeah. If the double bond were like coming off of the ring, that would be a different situation. We're not going to get into that. But because it's inside the ring, still we can follow both rules that way. Capture the whole thing and have the double bond in there. But yeah, that's a good question. All right, so see if you can name these last two. Take a stab at it, and then we'll look at them together. You would name those. Yeah.
Was that double bond in this picture? Double bond is on the 2, right? So
well, it goes between the 1 and the 2. Or you mean the last one?
No, I'm comparing the first one with the last one.
Yes, okay.
So at the first one, you started with 1 and 2, the double bond. Then you went to 5.
Yep.
Now the one at the end, you're starting with 1 and you're able to go to 6.
Yeah.
But you didn't start it with the double bond.
Right.
And what makes that different from you needing to start it with the 2 versus taking the whole structure on the last one?
Yeah, good question. You still always have to start at the end of a chain. So in this case, the double bond was at an end of a chain, so we could start at 1. But in this case, it wasn't. So we still start at the end, but we give the double bond the lowest possible number.
We have to decide that, like, if the one connected to the chain, then we have to start with that. If it's not, we need to start nearby there.
Right. You still always start at the end. You still always start with 1 at the end of a chain. At the end. And then you count from there. In this case, the end was also the beginning of a double bond, so it worked. In this case, it wasn't, so we had to start at a regular carbon and then get to the double bond as soon as we could. But we still always start numbering at the end of the chain. All right, does anybody want to give a try for a name in one of these? No. For the middle one, what's our main word here? Yeah, and more specifically, not just hexene, cyclohexene, because it's a ring. Cyclohexene. And we would add to that 3,3-dimethyl. And then let's see, just to be consistent, we can get it to work. Oh, there we go. We can put that 1 in there. Sometimes that 1 goes missing when it's 1, like it's assumed, but just to be consistent, we'll keep it in there. And this last one, the main name is going to be hexene. But because the double bond starts at 2 instead of 1, it's going to be 2-hexene. So you can have 1-hexene, 2-hexene, 3-hexene, and those would be different structures based on where the double bond starts. And then we add the 2 substituents, so this becomes 5,5-dimethyl. Because the double bond starts at 2. All right, so then the other thing we have to deal with sometimes with double bonds, and not all the times, but sometimes, is this issue of not being able to rotate. So we have names for that as well. Let's look a little bit closer at these 2 structures. Kind of like what we drew before. So what's the name of this? What's the name of these? So you got 4 carbons, so that's but something. What's the end going to be? Ene, because it's a double bond, so butene. So it's not, but it's not just butene. What else do we have to put in there? 2-butene, because the double bond starts at the 2nd carbon in from the end. So 1, 2, 3, 4. So this makes it 2-butene. And then the problem is that the other one is also 2-butene. We count it out the same way. Everything works out. The double bond starts at 2, so also 2-butene. Okay, that's a problem because these are different molecules. They're not the same. And if 2 molecules are not the same, then they shouldn't have the same name. So we need to make a way to specify that one of them has one orientation and the other one has the other one. And the way we do that is you draw or just imagine a line that runs parallel through the double bond. See that? Let me try to make it a little bit more like a dotted line like this, or a dashed line. Okay. So we think of the double bond as this like wall or something. If the things on the 2 different carbons are on opposite sides, we can call that one thing. And if they're on the same side, we can call that another thing. Do you see the difference in the 2 there, if I use that terminology? So here, carbons 1 and carbons 4, which are the carbons connected to the double bond, are on opposite sides of that line. And over here, they're on the same side of the line. See that? And that would be the case no matter how we rotated or did whatever. If we kept it, as long as we didn't rotate it, we can spin it and still have that same orientation. So the language we use for that is if they're on opposite sides of that line, we say that that's called trans 2-butene. Trans means opposite, so it's like they're on opposite sides of the line. And then if they're on the same side of the line, that's called cis 2-butene. Cis means same. So we can use this cis-trans language to talk about whether those are on the same side or on opposite sides. Now this works great for simpler structures like this. It stops working when there are more than two things connected. So if you had something like, I don't know, something like that, you can't say cis or trans because, like, okay, this one's on the same side as this one, but it's on the opposite side of this one, and then this one's opposite to this. So like there's too many different choices. So there's a different way we go about doing that. We're not going to go through it in this class. We can't use cis trans for a structure like that. There's another thing called E and Z, and that's beyond the scope of this class. Go take an organic class if you want to learn about it. But we can apply this to some, what? What? Oh, cis, CIS. Sorry, the pen is being a little weird. We can look at some bigger structures and still say the same things. For instance, this is this kind of giant molecule is called a saturated fatty acid. So when we talk about saturated fats, these are the types of molecules that those are made up of. And then if you have, that word saturated means the most, saturated always means the most possible of something, like the most you can have. And in fatty acid, it's the most possible hydrogens. So the most hydrogens you can have. So then if something is unsaturated, that means it has fewer hydrogens. And the way to do that is with double bonds. So what happens in these things, oops, kind of weird, is they get these double bonds. And this would be called a monounsaturated fatty acid. Because there's one place that it's unsaturated, the double bond. And then we also have polyunsaturated fatty acids, which have multiple double bonds around. But most of the double bonds in nature are cis double bonds. So if we draw that same line here, you can see that the things branching off are on the same side, right? See that? You can see those branches coming off the same side of that green line. So that makes it cis. And most naturally occurring unsaturated fatty acids have that cis geometry. This is why unsaturated fats tend to be liquid, like oils like olive oil, vegetable oil, whereas saturated fats tend to be solid, like butter, other animal fats, things like that, hydrogenated oils, because they can pack together more tightly and become solid and have a higher melting point. So because of that, they behave differently in the body, and we all know that unsaturated fats are generally better for you than saturated fats, but they're both important and okay in moderation. What is a problem is if you do a chemical procedure called partial hydrogenation, you can kind of stretch this thing out without getting rid of the double bond. And this is what we call trans fat, or a trans fatty acid, if you've heard that term. Fat is technically a triglyceride, so it's three of these things put together, kind of hooked together. with a glycerol molecule. So these are individual fatty acids. This is trans because, again, if we look at that double bond, we can see the branches come on opposite sides of that line that we drew. And this is a, there are trans fats that are naturally occurring, but for a long time they were used widely because it was discovered that, for one, they lasted a lot longer. They didn't go rancid as quickly because they could pack so tightly and they were solid. And also, they can advertise foods as having no saturated fat. So when saturated fat was this big like no-no in the 80s, I guess late 70s really, and 80s, it was you couldn't have saturated fat. Saturated fat was going to kill you. And so companies made these trans fats that behaved just like saturated fats, but were technically not saturated fats. And now we know they're actually way worse than saturated fats, and they're mostly not used at all anymore. It's rare that you'll find them. But they used to be in everything, from like French fries to this whole idea that like Twinkies last forever. Have you heard that? That's because they used to be made with boatloads of trans fats, which don't go rancid quickly, and so they can last really, really long times without turning rancid. And so, so that's where that comes from. But we know now that trans fats are really, really bad. So they tend to go in the same places that the saturated fats go, and then form even tighter plaques and clog arteries and cause other kinds of problems. So we don't really use them anymore. But that language all comes from the geometry that we've just been talking about. Okay. Feel good about this?
Can you do a problem where you write it out first and then you come up with the structure?
Yeah, like I give you the name,
Yeah.
and then you have to write the structure? Okay, let's do that. All right. So see if you can write a structure for cis 5-methyl-2-hexene. A little hint: when you see that cis or trans, don't worry about it at first. Write your structure just like you're going to write your structure. Then check it, and if it's wrong, then you can just flip one thing and have it be okay. You try to draw it that way first, it might screw everything else up for you. So just draw it the way you would normally draw it, then check the cis trans and change it if you need to change it. All right, we're almost out of time, so I'm going to go through how you would do this. So here's how I would do this. I would start with just the main part of that name, which is hex. I would just draw 6 carbons. 1, 2, 3, 4, 5, 6, just like on the quiz. Then you notice, okay, it's a hexene, and it's 2-hexene, so I got to put a double bond in there on carbon number 2. So that's going to be like that. Yeah. Then I can add that 5-methyl. So 1, 2, 3, 4, 5. There's my 5-methyl. And then finally, I look and correct for cis trans. So I kind of draw that line through the double bond and say, okay, are the two branching parts on the same side or opposite side? So what are they in the way I drew it? Opposite. You see them? They're on opposite sides of the green line. Like this thing and this thing are on opposite sides of that green line. So that makes it trans the way that I drew it. So that's trans. So that means I did it wrong compared to what's in the name. But that's okay, because all the rest of the structure is fine. So all I have to do is flip one side over to the other side of the line, and I've got it. So instead of putting it here, I'm going to put it there so that they're on the same side of the line. And then let's redraw that so it looks a little better. Which, by the way, you can do all this when you're drawing stuff. You don't have to just place it on paper beautifully done on the first try. You can mess with it and scratch stuff off and moves things around, and then correct it and make it look nice. So if I do that, now I've got that, and now I have the correct structure. Another hint, and with practice you'll see this, when we normally do our zigzagging, that almost always makes a trans double bond. So if you need it to be cis, you have to flip one side from the regular zigzagging.
Well, the one thing like this down.
What do you mean? Like how to number it? Oh, yeah, that works too, yeah. So you can flip the other side, and so it ends up going down too. Yeah. As long as they end up on the same side of the line, that's fine. All right, we're out of time. So we'll stop there and see you in about 15 minutes for lab.